Everybody, this is Group 5, and today we'll be discussing Chapter 9, or Quality and Statistical Process Control. So before I get started, some learning objectives that we'll learn today will be how to distinguish between common cause variation and assignable cause variation, and as well as input variables, environmental variables, and outcome variables. In 9.2, we'll learn how to compute the process capability index and defect probability. 9.3, we're going to learn how to construct a control chart and use it to determine if abnormal variation exists in a process. With 9.4, we'll learn how to create a fishbone diagram and a Pareto diagram. With 9.5, we'll explain how to avoid defects by creating a robust process. In 9.6, we're going to learn how to create an event tree to model defects. And finally, in 9.7, we're going to learn how to create a P-chart. So let's begin with 9.1, which is the Statistical Process Control Framework. So here are some key terms that are relevant to this section. Natural variation or common cause variation are the variation that occurs in a process as a result of pure randomness. Assignable cause variation is variation that occurs because of a specific change in input or in environmental variables, so it's not random at all. Input variables are the variables in a process that are under control management. Environmental variables are variables in a process that are not under control of management, but nevertheless might impact the outcome of the process. So something like rain or ocean, anything that the management can't control that is in the hands of the environment. Outcome variables measure the describing quality of the output of the process. Defective is a term to show if something's not corresponding to the specifications of the process. Set of the specifications is a set of rules that determine if the outcome variable of a unit is defective or not. And so a management might set a rule or set some specifications, and if the output does not match those specifications, then they can rule that it is defective. Continuing, a root cause for a defect is a change in an input or an environmental variable that has initiated a defect. And robust is the ability of a process to tolerate changes in an input and environmental variables without causing the outcomes to be defective. Statistical Process Control, or SPC, is a framework in operations management built around the empirical measurement and the statistical analysis of input, environmental, and outcome variables. Abnormal is a variation that is not behaving in line with past data and allows us to conclude that we are dealing with an assignable cause variation and are not just facing randomness in the form of common cause variation. So here we have figure 9.1, which is the framework of quality, and it shows how input variables go through a process and outcomes output variables. And within that process, environmental variables can come in the middle and add defects or add changes and completely give us a different output from what we expected. So for a variation in outcome to happen, we need to have some variation either in input or in environmental variables. So when diagnosing a defect or trying to find out what caused the defect, we need to find the input variable or environmental variable that caused the defect, or in other words, the root cause. The goal of the management is to keep variation small and design the process so that variation does not completely change output and cause a large variation in output. And so they also need to avoid assignable cause, which are changes that aren't random, and make sure that those variations, if they do occur, leads to little to no defect. And multiple input variables impact the outcome variable. And so what happens here is that the amount of variabilities that occur stack up and cause more defects or disasters. So we can see that here with the input variables, there's multiple x1, x2, x3, x4, x5. And then due to the environmental variables, all of these stacked up variables cause different outputs to occur. And so we end up with y1, y2, ym. And so what this shows is that multiple variables sometimes causes us to have either less outputs, or the outputs that we do get have multiple defects. Now, how can we figure out what's causing defects? So that's where the SPC comes in. And the SPC, to have control on this process, you need to follow these 4 steps. So you want to measure the current amount of outcome variation in the process and compare how this variation relates to the outcome specifications. So basically you want to look at what's happening into your process and how these outcomes are different from what your specifications was. And this determines what the capability of your process is. After that, you want to monitor the process and determine if the present observed variation actually conforms to the usual pattern. And if it doesn't, that's when you realize you've actually hit an assignable cause. And once you've hit an assignable cause, you want to work on ways to stop that from happening. Once you investigate the root cause of an assignable cause variation, you can find the input and environmental variables that cause the variation. And to make sure that you have control on your system, you want to avoid the reoccurrence of these variations in the future. And by changing the process, you can make sure that your process is robust, and that way future products will not be affected by it. So let's check our understanding. The cafeteria is serving chicken noodle soup today, which it sources from a distributor and then warms up locally in the kitchen. The soup now sits in a large bowl, and a server uses a large ladle to fill up the soup into smaller bowls handed out to the students. Consider the following variables: outside temperature, duration that the soup was heated before being put in the bowl, temperature of the soup in the student's bowl, temperature level to which the soup is warmed up, insulation of the bowl used for storing the soup, duration that the soup bowl is open when the server inserts the ladle to serve a student. So which of these variables are input variables, output variables, and environmental variables? So the input variables are duration that the soup was heated before being put in the bowl, temperature level to which the soup is warmed up, insulation of the bowl used for storing the soup, and the duration that the soup bowl is open when the server inserts the ladle to the student. And this is because we know that the output variable based on the question is what the student receives. So anything prior to what the student is getting are all input variables as to what kind of temperature that the student might get. So that would include all the things I just said. And that leaves the output variable to be the temperature of the soup in the student's bowl, so when the student gets it. And that only leaves the environmental variable to be the outside temperature, because it's something that the management can't control, and that also affects the temperature of the soup in the student's bowl. Let's continue on. Two students compare the amount of chicken meat they have in their chicken noodle soup. Student A has 2 times more meat than student B. The students debate whether this difference is a result of common cause variation or whether there exists assignable causes. Which would be examples of assignable causes? So before we begin, let's make sure we understand exactly what an assignable cause is. That is something that is not a random variation, so something that is in our control. And so some examples of assignable cause would be if the meat falls down into the soup because of its weight, and so all the children who are served first will get less meat, and maybe the children in the end will get more meat due to that. Or it can be any mistakes in production of the soup, or if the person serving the soup is not stirring the soup, so the chicken's not completely mixed into the entire soup. So all these things are assignable causes which would cause student A to have more meat than student B. With that being said, let's move on to 9.2.
Hi, my name is Hannah Rodriguez, and today I'll be covering section 9.2. In this section, there are 4 subsections, which are determining a capability index, predicting the probability of a defect, setting a variance reduction target, and process capability and summary and extensions. To start us off in section 9.2.1, there are 4 key terms. Lower specification limit, also known as LSL, which is the smallest outcome value that does not trigger a defective unit. On the flip side, there is also upper specification limit, which is the largest outcome value that does not trigger a defective unit. Process capability index, which is the ratio between the width of a specification interval of the outcome variable and the variation of the outcome variable. This is what shows us how many standard deviations we can move away from the statistical mean before causing a defect. And the last one would be the 6 sigma process, a process that has 6 standard deviations on either side of the mean and the specification limit. To further understand our key terms, here's an example. For a scooter, the ideal steel support would be 79.95 millimeters. If this steel support were to go below 79.9 millimeters, it would be too small. If the steel support went above 80 millimeters, it would be too large. The standard deviation would be 0.0172 millimeters. Looking at this information, we can infer that the LSL would be 79.9 millimeters because this is the lowest it can go before it does not fit. We can also infer that the upper specification limit would be 80 millimeters because that is the largest it can go before it does not fit. Given this information, what is the probability the process produces a defect? To figure this out, we would first need to know the formula for the process capacity index. This would be USL minus LSL over 6 times the standard deviation. So for this example, it would be 80 minus 79.9 over 6 times 0.0172. Here's another example which we can see our learning for the process capability index. You can stop here if you would like to try on your own, but I will be explaining it. A bottle filling process has a LSL of 0.99 liters and an USL of 1.01 liters. The standard deviation is 0.005 liter and the mean is 1 liter. What is the process capability index for the bottle filling process? So from this information, we can tell that the LSL is 0.99 and the USL is 1.01. We also know the standard deviation to be 0.005. So from this, we can fill out the equation. 1.01 minus 0.99 over 6 times 0.005. This would make the process capability index as 0.6667. Now to understand the Six Sigma process. If we assume that the mean of the normal distribution is in the middle here, we can determine we can go 3 standard deviations from this point before hitting the specification limit. So 1, 2, 3, and 1, 2, 3. Looking at the bottom figure here, the specification limits are the same. However, with this one, we are able to go 6 standard deviations in either direction, which would make it a 6 sigma process. Since the standard deviation is much smaller, the likelihood of a defect is also much smaller when compared to this one. Moving on to section 9.2.2. There are only 2 key terms in this section. Defect probability, which is the statistical probability with which a random chosen flow unit does not meet specifications, and parts per million, the expected number of defective parts and a random sample of 1 million. In this section, we will be using Excel, so you can open this alongside of it. To perform defect probability, there are 4 steps. The first step would be to find the probability that a unit falls below the LSL. This is done by entering norm.dist into Excel, which would be LSL, mean, standard deviation, and 1. The second step would be to find the probability that a unit is above the USL, which is done by entering 1 minus norm.dist into Excel. So USL, mean, standard deviation, and 1. The third step is once you find these totals, you would add them together to find the defect probability. And the fourth step, if you want to find parts per million, you would multiply this by 1 million. So this would be how you would find how many parts would be defective per million units. However, you do not need to use Excel, and you could also use the capability index to figure out parts per million. For example, in our example earlier, our capability index was 0.6667. So you would find that on the chart, and then you would cross-reference it with the rest of the row to figure out the parts per million. So for that one, 45,500.26 units would be defective per 1 million units. Moving on, experts recommend a minimum process capability of 1.33. However, now many companies are requiring that the process capability should be 2 at every step. This would mean that the USL is 6 standard deviations above the mean, and the LSL is 6 standard deviations below the mean, which is also a 6 sigma process. This process makes a defect with a very low probability, which would mean that there would only be around 2 defects per billion units. This is very, very small, especially when we compare it to the 1.33 process capability. The reason why companies are doing this is because even though it seems small, and even compared to the 1.33 looks small, but when you add them all together of all the parts, it really adds up. Again, moving on to section 9.23, there's only one key term: target variation. This is the largest amount of variation in a process that does not exceed a given defect probability. So to do this, we can do calculations starting with the desired defect probability and then computing the standard deviation in the process. We can do this by doing simple algebra. So looking at our question, we have: consider again our bottle filling process, which has a lower specification limit of 0.99 and an upper specification limit of 1.01. The standard deviation is 0.005 liter and the mean is 1 liter. The company now wants to reduce its defect probability from the previously computed 0.0455 to 0.001. To what level would they have to reduce the standard deviation in the process to meet this target? So again, we would enter it into the process capability index, but instead we would make the process capability index equal the 1.006. We would get that because we know that the ppm is 1000, so we would go back and reference our chart, and to find 1000 we would look at the ppm, and it is in between these two, so we can determine that we would want to use the 1.0667. After that, it's just simple algebra to figure out what the standard deviation would be. This is important because by rearranging, we are able to find the target variation of this. The last section is essentially a summary of the rest of the sections. So for the summary, we learned how to use specification limits of a process with standard deviation. We computed the process capability as well as the defect rate, and we found the target variation. However, important observations to remember is that even though we learned that a process has both an upper and lower limit, or lower specification limit, and the mean is right in the middle, this is not always the case. In some cases, there only is one specification limit, and the mean is also unlikely to be exactly in the middle. Thank you.
Hello everyone, my name is John Paulo Kimosing, and I will be covering section 9.3 of chapter 9, which is Conformance Analysis. We would start off with the key terms. The first key term is control charts. A control chart is a visual representation of variation in the process. Time would be on the x-axis and an outcome variable on the y-axis. In each time period, we collect a sample of outcomes, which we then plot in the control chart. The control chart also displays a long-run center line, also called the x-bar, which is the average across all points. It also shows an upper and a lower control limit, which are computed based on previous data. The next term is x-bar charts, which is a special control chart in which we track the mean of a sample, also known as x-bar. X-bar is then the average of a sample. The next term is the upper control limit, the UCL, which is a line in the control chart that provides the largest value that is still being acceptable without being labeled a normal variation. The next term is the lower control limit, otherwise known as the LCL, a line in the control chart that provides the smallest value that is still being accepted without being labeled an abnormal variation. The next term is the x-bar, which is the average of a set of sample averages. Estimated standard deviation of all parts is the standard deviation that is computed across all parts. The estimated standard deviation for x-bar is the standard deviation of a particular sample mean, which would be the x-bar. Then, looking at the left side of the slide, we see that there is table 9.2, which is the measurement of the steer support dimension in groups of 5 observations. Then, in order to compute x-bar, which is the mean of a sample consisting of n units, it would be x-bar equals x1 plus x2 plus x to the nth term over n, which is the number of units. Considering the data on the left side of the slide, the x-bar of data 14 will be computed by adding x1 plus x2 plus x3 plus x4 plus x5. Then we would divide that all by the number of units, which would be 5, and it would equal 79.972. After computing the mean for each period, we could then compute the average across all days, otherwise known as x-bar. And at the bottom of table 9.2, we see that the value is 79.951. On the left side of the slide, I included the example of a generic control chart. And as you can see, on the x-axis, you see the time periods, and on the y, you see the process parameter. And then you can also see the upper control limit on the top side of the chart, the center line, and the lower control limit on the lower side of the chart. Adding on to the previous slide, in creating the x-bar chart, you would use the computed value of x-bar as the center line and plot the values of x-bar for each day in the sample. Then, after we have the x-axis, the time periods, the y-axis, the mean, the samples for each period, and the center line, there's only one piece left, and that would be to find the control limits. To help find the control limits, we must first calculate an estimated standard deviation of all parts using Excel's standard deviation procedure. referring back to table 9.2, the estimated standard deviation for all parts is 0.017 846 388. And on the bottom of the slide, I included the standard deviation for all parts formula that we would use to find this. Moving on, for a given sample measurements, the estimated standard deviation for X bar, the estimated standard deviation of that sample mean, can be found through standard deviation of all parts divided by the square root of n, the number of terms. On the right side of the slide, I included the X bar chart for the steer support part that we have calculated. For the Zuder case, we compute the estimated standard deviation, which would be 0.0178 463.88 over square root of 5, which would then equal 0.007981147. We would call the process auto control if the sample is 3 standard deviations above or below the long-term mean. This leads to the following control limit calculations. Compute the upper control limit for X bar as UCL equals X bar plus 3 times the S standard deviation of X bar. As calculated, it would turn up to be 79.9749. Then we need to compute the lower control limit for X bar. As follows, it would be LCL equals X bar minus 3 times the estimated standard deviation of X bar, which would then equal 79.9271. With that said, a process that is behaving should have estimated sample mean fall between the LCL and the UCL in 99.7% of the cases. And control charts obtained this way allow for a more visual representation of the variation of the entire process. Check your understanding. Question. For 50 consecutive days, a process engineer has measured the weight of a component after it has been coated with a special plant. Each day, she takes a sample of 10 components. The average across all 500 components, 50 days, 10 components per day, is 45.343,018 grams. The standard deviation across all parts is 0.0076382 gram. When constructing an X bar chart, what would be the center line and what would be the lines for the upper and lower control limits? Simple. The center line was already given as it is 45.343018 grams. However, in order to find the control limits, we have to find the estimated standard deviation for the X bar sample. Again, the formula is as follows: standard deviation of all parts divided by the square root of n. N would be the number of terms. So by dividing 0.007632 by the number of square root of 10, we get 0.002415. With that value, we would then find the upper control limit and the lower control limit. And it is as follows. UCL equals X bar plus 3 times the estimated standard deviation of the X bar. And the value would be 45.35026. And the lower control limit is as follows. The LCL equals X bar minus 3 times the estimated standard deviation of X bar. And the value would turn up to be 45.33577. Thank you. All right.
Hi everybody, I'm Sam Sadian and I'll be discussing section 9.4 of chapter 9. So to start off, we have our key terms, which is fishbone diagram, 5 whys, and the Pareto diagram. The fishbone diagram is a structured way to brainstorm about the potential root causes that have led to a change in an outcome variable. More simply, it just helps map out all the input and environmental variables, and it's also known as the cause-effect diagram and the Ishiwaka diagram. The 5 whys is a brainstorming technique that helps employees find the root cause of the problem. The technique is asking, why did this happen 5 times, to help avoid stopping too early or not having found the real root cause. Finally, the Pareto diagram is a graphical way to identify the most important causes of process defects. It's similar to the fishbone diagram, just set up a little differently. First, you collect data on the number of defect occurrences as well as the associated defect types. That data is then used to plot simple bars with heights indicating the relative occurrences of the defect types. So this is an example of a fishbone diagram. As you can see here, under the cause section, there's things like slow computer, noisy workers, being out of pens, lack of planning, no timesheet, or sick children. And all these causes lead to the effect of missing a deadline. It's just a really easy way to lay out the different causes that essentially lead to an effect in your business. The 5 whys. This is an example of why a student came late. So the first question you ask is, why did you come late? And the student would reply that they wanted to grab a coffee. And then the student, we ask the student, why did you take so long to grab the coffee? And he or she replies, because the coffee shop is far from class. Why didn't you go to the close by coffee shop next to class? Because the coffee at the other coffee shop is better and cheaper. And so then we ask, why is the coffee shop that's close to class so overly expensive at offering bad coffee? And the answer is because they have a local monopoly and don't respond to customer needs. And then finally, our 5th question is, why does the local shop have a monopoly? And it's because the university decided to sell the coffee rights to a third party. And so as we see, with the 5 whys method, we went deeper, and instead of just saying, oh, why was the student late, we learned the root problem instead of just the surface level symptoms, which is, oh, he's being late, he's not responsible. It's also important to notice how the responsible party changed. It was initially the student, and then because we can see that it has more to do with the actual coffee shop and the university selling rights. Finally, we get to the Pareto diagram. This is, again, another way to just help identify causes. So as we can see here, it labels on the bottom different complaints like overpriced, small portions, food is tasteless, etc. And it nicely shows bars indicating how many times those complaints have been given. And this, in my opinion, is a little bit easier of a way to understand what your real problem is, or what the real cause of your problem is, because it's more laid out. You can see how many people are complaining for what. Like food not too fresh, only 9 people have complained, so it's probably not a very common occurrence. Whereas overpriced seems to be the main occurrence, which is probably something that the business should pay attention to or change. And yeah, 9.4 again, super simple, and that's how we address causes in a business. Thank you.
Hi, I'm Lizelle Kimbao, and I'm going to be talking about 9.5, which is how to eliminate assignable causes and make the process more robust. So talked about earlier in this chapter, variation in outcome variables such as geometry of a part of duration of a service activity is at the root of all quality problems. So to improve the quality, your first priority has to be to identify the source of variation and eliminate them. Eliminating variation such as human resources or human flow units can be difficult. So why don't we just learn to accommodate variations? Instead of fighting variations, why won't we just be more knowledgeable in finding ways to accommodate them? Find designs and ways of a process that won't fall apart nor have any defects. The terminology you want to remember from this section of the book is robust process. It is a process that can tolerate variation in input variables and environmental variables without an increase in variation in outcome. So there are three main common strategies that are used in this process, such as foolproofing, early signs on input and environmental variables, and overengineering. Like I've said, overengineering is one of the most common strategies, and it is to consider even the rare variations of input and environmental variables when determining things such as geometry. We want to make the process successful even in harsh, exceptional conditions. The example that they used in this book was that engineers determining how much rough water a ferry can handle before they depart, so that they know if they can depart or not given the certain weather condition. Another common strategy is foolproofing. It is to change the work so that the operator attempting to make a mistake won't be able to make one. One of the benefits for this one is that it can lead to the person learning from their mistakes and won't continue doing so in the future. The example that they used in the book for this one is changing the design of the syringe for oral medication delivery so that it can be unique and different from the rest of the IVs and syringes so that the caregivers may know the differences between the syringes and IVs and that it can just hinder them from making a mistake. The last and final one is early signs on input and environmental variables. It lies in the nature of a process that there typically exists some time lag between the occurrence of variations in input variables and environmental variables, and the occurrence of the variation in the outcome variable and the defect. The example that they used in the book for this one was the sinking of the MS Estonia, and it could have been prevented if the crew members not only focused on the harsh weather conditions that they knew beforehand, before the departure, but if they knew about the poor balance. If they knew about the poor balance, because poor balance played a main factor of the sinking of the MS Estonia. If they knew about the poor balance before they departed, they could have questioned whether or not to continue doing so or just balance it out. And that was 9.5. Thank you.
Hello, everyone. My name is Bishoy Sadek, and today I'm talking about Chapter 9, Section 6. The title of this section is called Defects with Binary Outcomes, and the main focus point is event trees. The outcome of the process is influenced by a set of input variables and environmental variables. Under certain conditions, we get a defective outcome. For now, we assume that the input variables, environmental variables, and the outcome variables just have two discrete values, and they can either be good or defective. And that basically means we're just gonna be focusing on two outcomes of all the examples that we're gonna be doing. And that means it could be either good, defective, and like in other cases, it could be on and off. And this analysis is used in many other areas. It basically analyzes all possible outcomes of certain processes. And for key terms, we only have one, and it's event tree, and it's basically a visual representation of binary outcomes that supports the defect probability calculation by connecting the defects in the process to an overall outcome measure. And the book provides two examples to help explain what binary outcomes are. So the first example is an assembly line example, and I like to call it good all the way. In this example, if we have an error or a defect in any of the steps during a process, the final outcome will be defective. And in order to have a good outcome, we have to have good outcomes in all steps. And this is basically like an assembly line. Let's say it's a car manufacturer, and it has 3 steps to manufacture a car. Step 1 is to assemble the body of the car. The second step is to put the engine in the car, and the third step is to install the electronics in the car. So in order to have a good car, a good product, we will have to do good in all 3 steps. So the body of the car needs to be good, the engine needs to be good, the electronics need to be good. But if we have a defect in any of the 3 steps, the final outcome, the final product will be defective. So the example we have here says, in the assembly of a simple component, there are 3 steps that potentially can lead to defects. The first step makes defects in 2% of the cases. The second step makes defects in 5% of the cases. The third makes defects in 3% of the cases. In order for the component to function correctly, all 3 steps have to be carried out correctly. In this case, in order for the component to function correctly, step 1 has to function correctly, and step 2 has to function correctly, and step 3 has to function correctly. So the probability of the component functioning correctly is given by probability of good unit, and that equals the probability of a good outcome in step 1 times the probability of a good outcome in step 2 times the probability of a good outcome in step 3. And since we are giving the probability of the defects, so we will simply do 1 minus the 2%, 1 minus the 5%, 1 minus the 3%. And if we do this simple calculation, we will end up with 0.90, which is 90% good unit. And if we want to know the defect probability, we will just do 100, which is 100% minus the percentage of a good outcome. And we will end up with 0.096. And the second example that we have is the medication delivery example. And I like to call this "there is hope." That means if there is an error somewhere in the process, but it gets caught, then we will end up with a good outcome. So if step 1 and step 2 in the process do a mistake, but step 3 catches it, this mistake will be fixed and we will end up with a good outcome. And so on. Because it's basically like a circle. So there is no start and there is no end. As long as the error gets caught, it will be fixed and we will end up with a good outcome. And the example we have here says, the pharmacy catches 70% of the mistakes that a doctor might make while writing a prescription. Next, the nurse sometimes double checks the medication with the attending physician, which catches another 80% of the mistakes. Finally, sometimes the patient herself alerts the nurse to the medication problem. However, that only happens in 50% of the cases. The medication example is fundamentally different from the first example. In the medication example, the process was more robust because as long as the medication mistake was caught at any of the 3 steps, the patient would not receive the incorrect medication. Put differently, in order for a defect to happen, all 3 steps would have to make the mistake, and which would happen with a probability of, and now we have the formula for probability defect. So to calculate the probability defect, we will calculate the probability defect at step 1 times the probability of defect at step 2 times the probability defect at step 3. And in that case, we got 70%, 80%, and 50%. So if we do 100% minus 70, we will get 0.3 and so on, 0.2, 0.5. So this is, we have 3% that we will end up with a defective outcome. And if we want to get the probability of ending up with a good outcome, we would simply do 100% minus the 3%, and we will get 97%. And this is what event trees look like. So here we have two event trees. The one on the left is for the assembly line example. And like I was saying earlier, if we find a defect at any step during the process, so we have 3 steps right here. That's the first step, second step, third step. So if we have one defect at any step of the process, we will end up with a defective outcome. So if we start with a defect, next step also has a defect, third step has a defect, we will end up with a defective outcome. And if we have a defect in the first step, but the second step has a good outcome, and the third step has a good outcome, we will also end up with a defective outcome. And the only way to have a good outcome is to not make any errors at any of the 3 steps. So first step has to have a good outcome, as well as the second step, as well as the third step. And this is the only possible way to end up with a good outcome. But in the other example, like it was mentioned, as long as the error gets caught, we will end up with a good outcome. That's why the probability of ending with a good outcome is much, much higher than the other example, the assembly line example. So for example, if the doctor makes an error, which is the first step, but the nurse or the pharmacy catches the error, and at this step, the error will be fixed. So even if the patient ends with a defective outcome, like let's say she doesn't realize that she's not receiving the correct medication, it will still end up with a good outcome because it was already fixed at the second step. And the only way to have a defective outcome is for all 3 steps, for the pharmacy, for the doctor, for the nurse or the pharmacy, and for the patient, to have defective outcomes. That's the only possible way to get a defective outcome. And the book also provides questions so we could test our understanding of how binary trees work and how to calculate the amount of defective outcomes or the probability of defective outcomes. The example says, or the question says, an insurance company hands out flyers which customers leave their contact email so that the insurance company can contact them later. These flyers are transcribed to a computer system. In the data entry operation, the typist reads the handwriting from the flyer. In 90% of the cases, the handwriting is read correctly. And in 0.5% of the cases, the typist makes a mistake and writes something different from what he had read on the flyer. Create an inventory, and what is the probability that the data are entered correctly. So this pretty much follows the assembly line example. So if an error happens somewhere, so if the person who's reading the flyer reads it incorrectly or enter it into the system incorrectly, we will have a defective outcome. So there is no place for error. And let's take a look at the answer. So this is the answer right here. So there are 2 variables with 2 outcomes each. And we are dealing, I believe this is a typo from the book. So this is 2 to the power of 2. So we have 2 processes or 2 steps in the process, and these two steps will lead to 4 different outcomes. So in order to have a good outcome, like I was saying, the person who's reading the flyer needs to read it correctly and also needs to enter the data correctly into the system. If an error happens somewhere, we will end up with a defective outcome. And to calculate the probability of the data entered correctly, we will do the probability of data read correctly times the data typed correctly. And that will be the 95% times the 0.5%. And that will give us a final result of 0.94% of data being entered correctly into the system. Okay, so that was 9.6, and I will leave it here to Omar to continue with 9.7. Thank you.
Good afternoon, class. My name is Omar Tovar, and I'm going to be presenting Chapter 9, Section 7, Defects with Binary Outcomes and P-charts. So just a quick recap on X-bar charts. This is very important for this section because it's going to be very similar to what we learned in a previous section. So this is an X-bar chart, and this X-bar chart is a specialized control chart in which we track the mean of a sample. This center green line is very important. This is the X double bar, and it's the average of set of sample averages. Okay, this X-axis is our time period in which we are working. Our Y-axis is our mean or average. This red line up here is our upper control limit, and this bottom red line is our lower control limit. So in this section, we encounter a problem with X-bar charts. These X-bar charts measure the outcome variable in a single dimension, and we use the intervals between the lower and upper control levels to be able to determine if a unit is defective or not. This no longer works for us because we're dealing with discrete outcomes. We can only distinguish defective units and non-defective units, which is something we don't need. So we are introduced to P-charts, which are special charts that are used with dealing with binary outcomes. It has all the same features as an X-bar chart, yet it does not require a continuous variable. However, P-charts do require large samples, especially if the defective rate is very low and rarely happens. This P-chart is also known as an attribute-based control chart. These P-charts usually range from 50 to 200 sample sizes for each period and can be larger, especially if it's a defect that happens less often. For example, right here, if our defect probability is 1%, the chances that we would detect this defect in a sample size of 5 or 10 is very small. So we would need a sample size more like 100 or 200 to effectively measure this. Samples are controlled in each period just as it is in the X-bar charts. So in order to find and be able to calculate our P-charts, we need to evaluate the percentage of defective items. This is denoted as P. This is the percentage of our defective rate, which is why it's also known as P-charts. We compute the average percentage of defective of all samples, which we call P-bar. This is the average across averages and is the center line attributed to our control chart, just as we used our X double bar in the X charts. So to compute the control limits, we first need to find our estimated standard deviation. And we find this by squaring the division between a percentage times 1 minus the percentage over the sample size. This will give us the estimated standard deviation. And in order to compute our upper control levels, we use P-bar plus 3 times our estimated standard deviation. And to calculate LCL, we get P-bar minus 3 times the estimated standard deviation. Keep in mind that if LCL is negative, we use 0 instead. Once we have created the center line in our lower and upper control limits, we use the P chart in exactly the same way as we would read an export chart. Every time period, we plot the percentage of defective items in the P chart. If the percentage goes above the upper control limit, we expect a negative assignable cause to be at work. If the percentage goes below the control unit, we expect some positive assignable cause to be at work. After all, the percentage of defects in this case goes down. So this is just a quick question to check your understanding. If you guys need, you guys can pause it right here, but I'm gonna read it to you guys. Every day, an online grocery store takes a sample of 200 packages that have been prepared and are now ready to be sent out to customers. Across all days, the average percentage of incorrect shipments is 3%. That's key. How would you create a P chart based on this information? So we first need to understand that it fits our sample size of being big of 200, and we have our 3% here. So I'm going to show you guys the answers. If you guys need, you guys can pause here. All right, so to first, we need to create our center line, which is at 3%. And then we need to compute our UCL and LCL. And we need to do the standard deviation. And our standard deviation of 3% would be 0.012 with a sample size of 200, obviously right here. And then since we understand what P bar is, 3%, we can plug it in and add 3 times our standard deviation to get a UCL of 0.066. On the other hand, our LCL is the same calculations except you subtract it, and this would give us a negative. But like I said before, if it's a negative, we use the line of 0 to as our LCL. Thank you.